Okay, can I have everybody's attention? I'd like to welcome our, this is our third Shapley lecture. This year we have Eric Linder. He's coming in to us from Berkeley Lab in University of California at Berkeley. And he has done a lot of work, and they have I guess, fairly large group there, which is doing computational studies in cosmology. They're looking at issues of dark energy, they're looking at dark matter, and a lot of the other really interesting things in the universe. And so with that, I will turn it over to Dr. Linder.
Okay. Thank you very much for inviting me to come here. It's always a pleasure to come to a place and give a Shapley lecture. So the Shapley lectures are ideally going to get everyone enthusiastic from the undergraduate level, graduate level, up to the professional research level to talk about some of what the latest results are, as well as reviewing how we put together our picture of astronomy, and in this case in particular, oops, wasn't supposed to go forward yet, put together our picture of the universe as a whole. So I'm going to talk mostly today about dark energy. Dark energy is really just a phrase that we use to talk about the fundamental physics that we don't understand, why the expansion of the universe is accelerating. So not only is the universe as a whole expanding, which we've known since the 1920s, but in the last dozen years we've realized that it's actually accelerating in its expansion. It's speeding up in such a way that you would not expect from conventional gravity. Gravity, of course, should be pulling things back together. It should slow down that expansion. So dark energy is definitely new physics, but we're not quite sure where to look for it yet. But let me start off with some older physics, and in particular to talk about the relation between the everyday world that we see around us and how that ties in with our study of the universe. You might think that cosmology is a subject very remote from everyday experience, and what I'm hoping to do is, in the next couple slides, is to show you that's really not so. That everything, when you look around you, is teaching you about the physics, and you're using those same laws of physics to understand the universe. So this is a picture of Berkeley Lab on a nice day, and you can barely see the Golden Gate Bridge out here. So you have San Francisco, Marin County, and here you have Berkeley. And one of the things that you notice if you go to work at Berkeley Lab is that there's a really steep hill that you have to go up to from campus to get up to. So Lawrence Berkeley National Laboratory, it's a U.S. Department of Energy laboratory. So there's a really steep hill that you have to go up to get there. And after you've done that, for a few days, weeks, etc., you keep wondering, well, why is this steep hill there in the way? And so you start wondering about things. And this is, of course, what scientists are very good at, that they haven't lost that curiosity that you have, that all children really have, of asking why is the world around us the way that it is. And so if you start asking this in a scientific way, why are there these steep hills, then you realize there are competing processes, competing forces. And so there are processes that build up the hills and there are processes that erode them away. And so, for example, building up, you gradually get led into the earth sciences, into geology. You learn about plate tectonics. In California, it's all too evident that you have plate tectonics. You have earthquakes every once in a while to remind you of these things. And so you have mountain building processes as plates collide together, for example. And so that picture was put together really in the 1960s. And then you continue to ask why. You continue to wonder, well, what is driving these plates to float around on the surface of the Earth, on the magma interior of the Earth? And you realize, well, something must be keeping the interior of the Earth in this liquid state, because the Earth should have just cooled down after 4.5 billion years. And so there has to be some heat process there. And you're immediately led into the subatomic processes. You're led into the radioactive decay of atoms as the thing that's generating new heat in the Earth's core, keeping the mantle molten, and then letting these plates float around and build up these steep hills. So you're led right away to one of the fundamental forces of physics, the weak force of nuclear decay, when you ask, why is there this steep hill in the way? You can ask about the erosive processes. The erosive processes, rain, wind, landslides, and so forth, are driven by the weather. They're driven by the climate. And where is the energy source for all that? Well, all of that energy source is coming from the sun. Okay? The sun is what drives the climate, drives the wind and the rain and so forth. And so again, you continue to ask why. You continue to wonder, and you can say, well, what is the physical process responsible for the sun, for all the solar energy that is coming to Earth? And so again, you're led to the subatomic scales, you're led to the strong force of physics, of nuclear physics, where you have fusion between atoms going on, providing the energy source in the center of the sun. And so when we look at the world around us, we're led to the subatomic world. And then we're also going to be led outward into the universe as well. So we immediately have the weak force and the strong force that we're dealing with here. But then you can continue to ask why. And you can say, well, where the atoms that are undergoing radioactive decay, these heavier elements higher up in the periodic table than the light elements, the hydrogen gas, the hydrogen, helium, oxygen, etc. You have the radioactive decay of the heavier elements in the Earth's core. And you can ask, well, where did the sun itself come from? Which is primarily the hydrogen and the helium. So the whole periodic table, where does that come from? And now you're led out into the universe. You're led out into the question of how do stars form? How does matter accrete together and eventually, if it's dense enough, undergo the thermonuclear fusion to create stars? And when you ask where stars come from, you're led into, well, how do stars aggregate together? What is the larger scale structure? So the galactic structure. What is the structure of our own Milky Way? What are the other galaxies like in the universe? How many galaxies are there? Are there assemblages of structures even larger than galaxies? And what happens when you get to the entire universe? And so again, from the everyday, you're led both to the subatomic scales and you're led out into the universe. And so immediately, from just why am I walking up this steep hill, you have the four fundamental forces of physics. You have the strong nuclear force that's causing the fusion. You have the weak nuclear force that's causing the radioactive decay, keeping the Earth hot. You have gravity, of course. That's what makes it difficult walking up that steep hill. And that's what brings together these atoms to form stars and galaxies and so forth. And of course, you have electromagnetic forces as well, which is probably the most familiar to your physics studies. And so, again, I want to just get this point that there really is no division between the human world and the physical world and the universe as a whole. And so this is one of the great joys of studying physics, that you can look at almost anything and say, okay, we can figure out through the laws of physics why this is happening. So one of the other things, I talked here about the spatial aspects of it, okay, the steep hills, how did the atoms get together? There's also the time aspects to this. How do things change over time? How do things evolve? And so why is the Earth the way it is today? We talked about mountains being built up and being eroded away. So there's obviously an evolutionary process there. But we know that the surface of the Earth was, of course, very different. We know that the Earth has only been around for so long. The sun had to form at some point. There's evolution throughout the universe process. So as far as life goes, why are we here to walk around? Then we're led into the molecular aspects, chemistry and biology. DNA, where did that come from? And how does evolution happen on that scale? It happens through mutations. One of the ways you can get mutations are through high-energy particles from outer space, cosmic rays. And I always like this picture because it looks like one of the cosmic rays is hitting right on Berkeley. And if you hang around Berkeley a lot, you realize that, yes, there's a lot of mutations going on. But then, of course, you ask, where are these high-energy particles zipping to the Earth from outer space? Where are those coming from? Well, they come from the deaths of stars. When stars go nova or supernova, you have acceleration of particles by the shock waves, by the very high electromagnetic fields in these processes. And so, again, when you ask about life on Earth, you're immediately led out again into the universe. Where the molecules originally came from, how those molecules change over time, is due to the dynamical processes in cosmology in the universe as a whole. Remember, the subtitle of this talk had dinosaurs in it, so I'm going to, by the end of the talk, you'll understand what dinosaurs have to do with dark energy. But here's the first appearance of dinosaurs. So, of course, life as exists in this room did not exist in the early part of the Earth's history. There was a period when you had the dinosaurs walking around. And so again, what's the evolutionary process that led from the dinosaurs going extinct and then having mammals come domination instead. And so the theory that arose in the early 1980s and has really been borne out by quite a substantial amount of evidence since then is that it was caused by a process where a asteroid collided with the Earth in some way that this could have given rise to volcanism. It could have given rise to basically a very long, years-long winter where so much dust was thrown up that plants couldn't photosynthesize and that a lot of life died out. And then you can ask, well, why did an asteroid, why did it collide with the Earth? Where did the asteroid come from? And why did it intersect the path of the Earth? And so then you're led out into solar system dynamics, to planetary science, understanding the origin of our solar system, the planets, the leftover bits, the asteroids, and so forth, and then what can perturb these orbits. And so then, when you ask what can perturb a solar system, you have to ask about things nearby. So nearby solar systems, for example, and you have to understand galactic dynamics. How does the galaxy as a whole evolve as well? And so you're led out eventually to the very largest scale structures, the universe as a whole, and the dynamics of that. So the fact that it's not static, but that it is actually undergoing this expansion. And so those two basic ideas of the human world is tied to the universe as a whole, and that dynamics happens on all scales, including on the universe scales, on the cosmic scales, are the two, I think, most fundamental things to understand about cosmology. So a picture of our universe this is a computer simulation. I'll play it a couple of times. And when you look at it, you'll understand that there's two distinct processes that are going on. So the first thing you saw is you saw a fairly uniform background that was expanding. So most movies that you see of simulations have taken out the expansion by hand, basically, when they show you the movies. So you saw that initial very strong expansion, but now what you're seeing at the end is you're seeing gravitational attraction where larger objects build up out of smaller objects. So let me play that again. Again, you have that expansion. It starts off very uniform, and then things, even as the expansion continues, it continues throughout the movie, little objects are gradually getting accreted onto larger and larger objects. So they'll come together, and that's how you build up from the stellar scales to the globular cluster scales to galactic scales, groups of galaxies, clusters of galaxies, and so forth. So you have that expansion, but you also have the gravitational attraction that counteracts it, and that brings objects together. It's also important to remember that when we look out in time, we're not seeing the universe the way it is now, but we're seeing the way it was in the past. And this is actually a much more familiar concept than you sometimes realize, the fact that distance is time, that astronomy is a time machine. It's the same thing when you get a postcard. I'm sure nowadays no one gets postcards from friends on vacation. They all text you or you're always in contact on your cell phones anyway. But pretend people still do postcards. When a friend sends you a postcard, you have no idea what they're actually doing at that moment. If they're sitting on the beach at that moment, they're telling you the way life was when they wrote the postcard, which was a couple of days in the past. As they travel further and further, the information you're getting about their state, about their environment, is older and older. You're looking back in the past more and more. And astronomers have exactly the same thing, where as we look at more and more distant stars and galaxies and so forth, it's basically postcards from the past. We don't know what's going on right now on some distant galaxy, but we're looking back the way it was earlier in the history of the universe. And that's simply because the speed of light is not infinite. If it were, then we could learn about things instantaneously. But it travels at a finite speed. When you look out 100 million light years in distance, you're seeing the way it was 100 million years ago. The way that it works out. And so we're basically seeing the universe at many different stages in its history as we use more and more powerful telescopes. And that lets us build up the picture of the history of the universe. So one of the goals of cosmology is to map out what our history is like. You can think of it like an archaeologist. They're digging down through the layers to understand what a civilization was like at various epochs in the past. So astronomers are doing that same thing. Now, of course, we are simply receiving information. We can't go out there and actually dig through the things. But as we build better and better telescopes, better and better technology, detectors, for example, to see even fainter levels of light, then we can dig deeper and deeper into the past. And if we ask what was the environment like in the universe in the past, then we can do that in a very similar way to understand if we ask the question, what was the climate of the Earth like in the past? Again, if we want to know what the climate was like 500 years ago, 1,000 years ago, 1,500 years ago, then we need evidence from the past to do that. And one way you can do that is, of course, through tree rings, where you look at the tree rings and you say, okay, well, these tree rings have different widths. Okay? Perhaps a year was especially cold or especially dry, and the tree wouldn't have grown as much. Or maybe it was very warm and very wet, and it would grow much more. And so, gradually, as you calibrate that sort of calendar back in time, then people who use tree rings to understand the Earth's climate can build up a very accurate picture of what the Earth's climate was, what the environment of that tree was, basically. So by the width, by basically how quickly the tree grew, then you can learn something about the environment, the climate environment. So what astronomers try to do is, you can't look at how quickly something has grown, but you look at how quickly the universe expands. And so you want to look at an object, a very bright object, because you want to see it all the way back in time, or all the way across the universe equivalently. And so we use exploding stars called supernovae, which can become as bright as an entire galaxy for a fairly brief period of time. And by looking at the distances between these supernovae compared to their redshifts, a measure of the expansion rate of the universe, then we get an analogous picture to the tree ring picture as we map out through supernovae what basically the distance versus redshift relation is, how quickly the universe is expanding. So instead of the climate history, we're learning about the expansion history of the universe. So people have tried to use supernova for a couple of decades. The last decade, people have gotten really good at it. And this is what discovered the fact that the universe is not only expanding, but the expansion is accelerating. And I'll get back to that in more detail. So this is a picture from the Hubble Space Telescope here. And so this is what it's like to look back in the past 10 billion years. So this is a field called the Hubble Deep Field. So the Hubble Space Telescope in orbit around the Earth stared at one part of the sky for quite a few orbits. You can build up a very deep picture, very faint objects. And all these tiny little objects that you see, all these faint little blue objects, for example, those are all galaxies, just at immense distances, going back about 10 billion years in the history. So basically everything in this field is a galaxy. So we, of course, can't see this with our naked eye. We can only see a few thousand stars in our own galaxy. But with telescopes, you can see other galaxies. And with space telescopes, you can really see quite dramatically far back. So I'm now going to show a little movie that zooms in on a small part of this field where the furthest supernova that we know exploded a long time ago. We first saw it in 1997. So it starts off with an artist concept and then it goes to real data. There's the supernova going off in a galaxy. It fades away. Now we're going to go to real data. We're going to zoom in on that galaxy from the Hubble Deep Field. So again, this is to give you a sense that when we're talking about the incredibly distant universe, let's start it over, okay. When we're talking about the incredibly distant universe, that is actually tied to things that we do know about the world around us. So you saw that that field that the Hubble Space Telescope observed is actually not far off from the Big Dipper, which on a clear night at least you can go out and see for yourself. And so again, the things that we experience around us are intimately related to the deepest questions that we're asking about the universe. So again, the universe is not something we can bring into our laboratory and experiment with the way we can in many other fields of physics. So how do we actually go about and learn and do real science with this? Make theories, test them, make predictions, and then test them against the data. We have to pretty much let the data come to us, although of course we devise instruments to single out specific types of data. So the three main pillars of cosmology is the observation with telescopes on Earth and in space, theory, just a lot of thinking, and the computational, using the fact that computers can crunch numbers much faster than we can to do simulations, constrained simulations using the laws of physics to understand how processes work. And so here, this is a telescope on Mauna Kea in Hawaii. This is the Planck telescope that was launched last May into orbit around the Earth-Sun L2 point. And then on the theory side, I think those are both pretty familiar to you. And then in computation, these are gravitational simulations where you zoom in. So each panel is zooming in closer and closer to this large simulation. And now you're simulating on smaller scales. So you try to understand things from clusters of galaxies, down to individual star formations. And of course, to do that, you have to use supercomputers. You can do a certain amount on laptops, but you also need these supercomputer centers. And Texas is, of course, very fortunate and very famous to have one of the best supercomputer centers in the country. So let me talk a little bit more in the next several slides about supernova in particular. Remember, there are guideposts to the expansion in the same way that tree rings let us know about the past history of the Earth. So, again, you have to blend together that theory, computation, and observation part of things. And so, for the students in the audience, it's very rare for someone to do all three of these things together. If you're interested in all three, you're good at all three, you're going to rise very quickly, very high up, because it's such a rare combination. But there are people who are very focused on the instruments, people very focused on the computers, on the theory, and they all have roles to play, and a good group will bring those all together. So to actually make progress, you really need all of those aspects together. So this is, for example, a spectrograph. So this is an instrument that breaks light up into the individual wavelength lines, the spectra, and you need people who can build instruments like that, put them on the telescopes on the best astronomical sites on Earth, such as this telescope in Hawaii. Here's a telescope that's down San Jose, California, which scans a very wide part of the sky. It doesn't go very deep, but it scans it very often. It picks up a lot of supernovae. Here's the Mauna Kea Observatory on top of a volcano in Hawaii. Astronomers very rarely go to the telescopes nowadays. You never look through an eyepiece. Okay, it's always done on your computer screen. And if it's done on your computer screen, you should ask, well, why should I climb up to a snowy mountaintop to do it? Why can't I sit down on the tropical beach in Hawaii instead and use my laptop to see what the telescope is seeing? And so here are some of our graduate students, and we're even cheaper than doing that, sending them to a beach in Hawaii to observe. We put them in a basement room at Berkeley Lab, but we put a poster of Hawaii on the wall, and then we tell them to observe, and let them pretend that they're in Hawaii. To be fair, they actually do go to Hawaii several times, because when you put a new instrument on, you have to actually bring the instrument there, you have to go through the whole calibration procedure. There's always someone on the mountaintop. There are special astronomers who basically spend all their time helping other observers get their observations done in the best way. But generally, a lot of work is actually done on the computers now. And then what you end up with is many detections of supernovae. So here's a little mosaic of some 30-some supernovae. This particular experiment, called the Supernova Factory, has detected around 400 supernovae so far. And then you have to crunch all those numbers with a supercomputer to learn about the specific characteristics of the supernovae. If you want to use them as distance indicators, you have to make sure that you understand the astrophysics. Is there something special about that explosion that meant that you can't use it as cleanly as you would like as a distance indicator? And I'll explain how that's done in a little bit as well. So one of the wonderful things about science in general is the predictions of doom, of the end of science, that, well, we've pretty much done all the easy stuff, and now what's left is so hard, we're just never going to be able to figure it out. So there's this famous quote by Auguste Comte in 1835, who said, we can't bring a star into our laboratory. How are we ever going to know what a star is really made of? How can astronomy ever be a science? You just can't do experiments directly on it. So he said, we'll never be able to know the composition of stars. And the wonderful thing about science is how quickly these predictions of doom fail. So it was 14 years later that the answer was found. So Kirchhoff, and many of you will have heard in your physics classes about Kirchhoff's laws, for example. Kirchhoff realized that the spectrum, the electromagnetic spectrum of an object, carries with it information on its composition. We look at the spectrum of the sun, we look at the spectrum of stars in our galaxy, the spectrum of distant galaxies, and we can learn what they're made of. We can learn about their elements, we can learn about their temperatures, we can learn about the surface gravity of the stars. There's a huge variety of information that's carried to us for free by the photons, by the light from those objects. So if you ever hear people saying, oh, well, we're never going to figure out that puzzle, then wait 14 years and there's a good chance. And again, we're hoping that the students in the audience are the ones who, they make their careers out of solving these mysteries, of actually going forward and being the ones to solve those. So, again, you have everyday experience with the equivalent of electromagnetic spectrum, where you have some sort of a code. So here's a can. You're not sure what's in that can, and the writing on the can, assuming you can read the writing, is in a language you don't know. So you have no idea at all what's in that can, but it has a barcode. Okay? It comes with its own spectral fingerprint, basically. So you go to the supermarket checkout, nobody opens up the can, does experiments, and says, okay, what you have here is a can of peas or whatever it is, and they know what to charge you. They look at that barcode, and they know exactly what is in that can and what the properties of it are. And so astronomers do exactly the same thing. Okay? You look at a spectrum, you look at the bright and the dark lines that you see when you basically put the light through a prism, you look at the individual wavelengths, and you can understand the composition. Again, you understand the elements, the temperatures, and so forth. So another analogy that you might have heard of is a very, very famous story from early Greek times, where Archimedes is brought in front of the king. The king says, my goldsmith made this wonderful crown for me, but how do I know they're not cheating me? How do I know that it's really solid gold? How do I know what the composition of this is, the interior part of it is, without breaking it apart and looking at it? How can I possibly know that? And Aristotle came up with his eureka moment, where he realized that we can learn things from the displacement of water that can tell you something about the volume, you can learn things about the weight, so therefore you can learn about the density. So you can learn about the internal structure of objects without actually breaking them apart. Okay? So again, astronomers use this all the time to learn about the composition of very distant objects. So now let me slowly work my way toward the dinosaurs again and talk about this very interesting scientific chain that happened. And again, the main lesson here is not the specific chain of events, but that science is serendipitous. That you cannot just sit someone down and say, find the solution to this problem. Okay? Science really doesn't always work on demand like that. You have lots of clever ideas. Some don't work out, some do. Some it's just not ready, the technology's not ready, whatever. But science in a theoretical sense, you never know what will end up being useful. Quantum mechanics, no one had any idea that it would lead to the transistors, to computers, and so on and so forth. General relativity, no one had any idea would lead to GPS, to satellites, and all of that. So a lot of fundamental science is done because you just are curious. You want to know about the world around you. So let me talk about this very unusual chain for how we learned about dark energy from basically starting off with Archimedes' crown. So again, we wanted to know what was inside of Archimedes' crown without breaking it apart. So there was this very clever, very famous particle physicist called Louis Alvarez at Berkeley in the 1950s, 1960s, 70s, 80s. And he was very curious about things. So remember those high-energy particles from outer space, the things that caused mutations in DNA and caused evolution, genetic evolution? So Louis Alvarez had studied those particles, those cosmic rays, studied particles in the early particle accelerators, and he said, I bet we can use those. We're getting these particles coming in from outer space, and they pass through pretty much anything. Okay? Eventually they get absorbed, and we can figure out how much material is in the way by figuring out how much they are absorbed. So we can put a counter in one place, and we can ask, all right, how many of these cosmic ray particles, in this particular case it was muons, mu mesons, we can ask how many are absorbed. And that tells us about the amount of material. Now, if you just have it on the surface of the Earth, then you get a certain rate. If you put it down deep in a mine, you'll get a lower rate because a lot is absorbed by the rocks around it. So his idea was, let's put it in the center of the Great Pyramids of Egypt. Because archaeologists were wondering, are there secret chambers in the pyramids? Are there burial chambers? Are there artifacts things that would tell us about the culture of the ancient Egyptians. But of course, no one's going to let you take apart the pyramid brick by brick to see what's inside it. So you have to have a non-destructive way of understanding what's going on in an object. You can't do the lab experiment. You have to be more clever, and Louis Alvarez was more clever. So there actually was a chamber node down in the center of the pyramid. So he put this muon counter, this cosmic ray counter, and counted the number of cosmic rays that come in from various directions. And calculated, does this match up with having a solid stone all the way through, or if there were more muons, that means they were absorbed less, and that there would be a gap somewhere, there'd be a hidden chamber. It turned out he didn't find any hidden chambers, or rather, he found that there were no hidden chambers. Again, in science, there's two very different meanings to that we didn't find any, or we found that there were none. Okay? So again, in science, no results are sometimes very important things to have. So Louis Alvarez went on to win the Nobel Prize, not for the pyramid experiment, but for particle physics. And he had a very famous research group at Berkeley that's now going to lead directly into our story. So in 1980, Louis' son was a geologist, Walter Alvarez, and he received his son, being a geologist, did field work all over the world, and he came back one day with a rock from Italy, and he gave it to Louis as a paperweight. And they noticed that there was this very striking layer in the middle of the rock, which was different from the surrounding area. And they found out that this rock was particularly high in iridium. Iridium is a particular element, but the thing is that iridium is actually not very common on the Earth. You find it a lot in meteorites. It's sort of left over from the process by which the planets were formed. And so what was all this iridium doing on Earth if there really isn't that much iridium on Earth? And why was it concentrated in this little layer? So they were able to date this layer back to about 65 million years ago. And sort of wondering, well, all right, is there anything special that happened 65 million years ago? So this has been very well known in paleontology, that this is a boundary between two major epochs in the two major periods in the history of life on Earth, the Cretaceous and the Tertiary periods. So this was called the KT boundary. And so it seemed like this iridium layer was pretty much at the same time as this KT transition, this transition between periods of life on Earth. And in particular, the dinosaurs died out essentially 65 million years ago, or at least many, many species of dinosaurs died out then. And so they were encouraged to pursue this further. And again, one of the wonderful things about science, about physics, is that your colleagues are incredible resources to work with. So you may be doing astronomy, or in Louis Alvarez's course, you may be doing particle physics, but then you know someone who does geology, in this case your son, and then he had friends over in nuclear chemistry, so they were extremely good at measuring very tiny proportions of elements, so they could really figure out the concentration of iridium in these layers. And they found these layers all over the world. And so you built together this team to look at this, and they followed it up. You might think, oh, well, it's just, some curiosity that, they could have let it drop, but no, they pursued it. And you look here at the Cretaceous and the Tertiary period here, and then on the iridium abundance is on the x-axis, and you can see there's this huge spike in iridium at 65 million years ago in the rock layers. And remember, iridium really doesn't occur very frequently on the Earth's surface. And so it seemed like a whole bunch of iridium got dropped on the Earth from outside the Earth, such as an asteroid hitting. So that was very suggestive. So the idea was maybe there was a large asteroid that impacted the Earth. You should be able to find the crater somewhere on the Earth, and that this could cause the extinction of the dinosaurs through the process that I talked about, where you shut off photosynthesis basically from the huge amount of dust that's run off. So I'm not going to go through the whole chain where this has actually been verified, where they actually discovered the crater off the Yucatan coast, so not too far from here in the Gulf of Mexico, and so forth. And then they continued to ask why. So again, the hallmark of a great scientist is just continuing to ask why. What leads to the next thing? So they ask, well, okay, was it just coincidence that the asteroid happened to hit the Earth then? What about, were there other extinction periods in the history of the Earth? And so they decided, let's look at the periods of extinction. And so here's the age before the presence of the Earth, and here's the extinction of families of creatures, so species, groups, families, and so forth. And the arrows mark, so the solid line shows the number, basically, of families that went extinct. And then the arrows show, suppose you did a periodic analysis, a harmonic analysis, at a particular period. What's the period that best fits? They found 26 million years. And you can see it pretty much hits most of the major peaks. Occasionally, there's nothing really going on there. Okay? But it seems to be pretty good. And so they started to wonder about this and said, maybe there's some event that every 26 million years perturbs the orbits in the solar system and causes an asteroid to come into the solar system. Most are, of course, going to miss the Earth. The Earth's a pretty small target. But occasionally you will get one to hit the Earth, causing these extinctions. So this was the question that they asked. Could this be plausible? You ask the question, you then do the experiment, or at least make the observations. So one of the physicists in Louis Alvarez's group, Rich Muller, invented an explanation for this. He said, suppose that there was another star very, very far out, orbiting the sun. So not part of the solar system. It's much too far out for that, but it occasionally perturbs the orbits of the outer solar system. So he called it Nemesis, or the Death Star. A very good book title. He actually did write a book on this. So the idea is you have the sun in here, all the planets are near the sun, and then you have the outer Oort cloud, the cometary cloud, basically, way out here, and then you have the star in a highly elliptical orbit. And so it comes out, it comes around, and occasionally it'll be out here and it'll perturb the orbits, causing these comet fragments to fall into the inner solar system. And so again, okay, you have an explanation, you've got to actually test it. So what's the next step? The next step is find a student to do your work. We're all familiar with that. So he found a graduate student called Sol Perlmutter, and for his PhD thesis, he automated a telescope. So again, this was back in the mid-1980s, where you tended to actually go to the telescope, you would point the telescope at a particular object on the sky, you would look through it. Okay? It was really very new at that point to automate telescopes to actually carry out a search night after night of a particular field of the sky. So he went out and he automated this to look where Nemesis would have to be in order to cause these objects to fall into the inner solar system. So he did not find Nemesis, and in fact, again, it's not just not finding it, but it's putting limits on something. It's finding that there was no Nemesis. And so to this date, there's no explanation for if there is a 26 million year period, what causes it. Most people, I think, no longer think that there really is that 26 million year period of extinction, that yes, it matched up in a number of cases, but it missed in a number of cases also. So it's sort of unproven, and not too many people are really pursuing it. But this automatic scanning of the sky turned out to be a major technological advance that was good for a lot of other things in astronomy. And so you scan the sky over and over again. What do you see? Well, most things just stay in place. Things that move are things like comets, asteroids, and supernovae. They don't move, but they brighten and then they fade away. And so it's not only good for finding moving objects, but it's finding the transient universe, the exploding parts of the universe. So a lot of hard work then went into this from the mid-1980s till the end of the 1990s. Okay? So here's Sol. He automated this Leuschner Observatory, which is just on the hills at Berkeley. It's not a great telescope site. There's a lot of light from San Francisco and so forth. But it was good enough at the time to do this. So again, let me remind you of this very bizarre chain of events, of scientific reasoning and of pursuit and of bringing all these different fields of science together. Started off by asking, are there hidden chambers in the Great Pyramid of Egypt? Louis Alvarez figured, we can use these cosmic rays, these particles given to us for free from the universe. By chance, he was given a rock by his son, which had a strange chemical layer, an Iridium layer in it. They realized that it was dated to 65 million years ago when the dinosaurs went extinct. They wondered, I wonder if that's a periodic event. They hypothesized, the group hypothesized then, that maybe there's something perturbing the solar system, a companion star. They automated telescopes to look for this, And they didn't find that, but instead they found that they had made something that's perfect for looking at the changing universe, the exploding stars in the universe, the supernovae. And again, supernovae are so bright, they're good for mapping out the universe, just the way tree rings map out the Earth's climate. So again, by 1998, you had built up enough supernova to map out that expansion history of the universe. So this is a diagram of basically the time before the present. So we sit up here, now we're looking back into the past, and the average distance. So as the universe expands, the distance between galaxies increases. So you start off about 14 billion years ago, and the universe goes up. So if you think of this as the trajectory of a ball that you throw on the Earth, okay, so this is time, and this is distance, or you can think of it as height, you know what the trajectory will be. The ball will go up, it'll reach a peak, and then it'll come back down. Okay? That happens in distance if I throw a ball across the room, but it's also a slice in time. As I throw the ball, time marches on, the ball goes up, the ball comes down. So the expectation was that you'd see a curve like this green curve, where it goes up, it peaks, it could be peaking in the future, and then it will come down. But instead, the data didn't fit that at all. The data of the supernovae, so what's the distance between the galaxies, mapping out this expansion history as a function of time back, the data fit this red curve, where you don't always have deceleration, where the curve turns over. It looks like you have a time with acceleration, where the curve turns up, where I throw that ball up in the air, and then somehow the ball speeds up and shoots off into the sky, which generally doesn't happen when you throw a baseball or something. So there was something going on. Gravity, of course, should bend it back down, should bring it back down. So this was one of the great mysteries. And this was labeled in 1998 as Science Magazine's Breakthrough of the Year, that this was just so fundamental that it changed our picture of the universe. We knew it was expanding, but why is it accelerating? What is causing it to speed up? It has to be something that doesn't act like gravity acts normally. And so it was really a new mystery within physics. So there was actually another team that did it. This is another very important lesson from science, that competition is actually really good. Okay? You get a result, you want your competitors to check that result as well. Okay? You want to get it first, of course, but you still want the other people to be able to check it and hopefully come up with the same thing so that you know that the answer is correct. Because if you get an answer once and nobody else can reproduce it, then that's not science. No one is going to believe that. So there were fortunately two teams working at about the same time on this, and they both did discover the same thing, this speeding up. So the real big question is, what is counteracting gravity? And here's that cover of Science that I talked about, the breakthrough of the year, where Einstein is looking very surprised. Well, what happened to his theory? I thought he thought that the universe should collapse again under gravity. So Einstein is now not pleased by this situation, and so it's up to modern physicists to now figure out, well, what is causing this? So let's go back to basics and ask, well, what could cause this? Is there something within Einstein's relativity that could cause this? So the key equation is one that's familiar to everyone, E equals mc squared. Energy is related to mass. So the key thing to recognize is that gravity counts all forms of energy. It doesn't only count the mass of this, but it also counts what the velocity of this is. It counts the internal energy, what's going on inside of this, and so forth. Every form of energy, kinetic energy, potential energy, chemical energy, that all contributes to gravity. So all forms of energy contribute to mass, contribute to gravity, which feels mass, of course. But one particular form of energy is pressure. So you might think, well, all right, if I'm adding things to the mass, shouldn't that just make the gravity stronger, make the universe collapse even sooner? And that's true, unless you can make the pressure negative. So we don't know of any way of making mass negative, but how about these other forms of energy? Can we make them negative at all? So you can ask, well, does that make any sense to even talk about negative pressure? And again, going back to the things that you know about in everyday life, you actually know several instances where there is essentially negative pressure. When something expands, then generally it will cool down. You open the door to your oven, the hot air inside expands out into the room, it cools down. If you expand a spring or a rubber band, for example, though, it doesn't cool down, it heats up. And so this is an experiment you can do. You can do the experiment both ways. The air in your lungs is hot, body temperature. When it comes out of your mouth, it cools down. So if you hold your fingers up in front of your mouth and you breathe out with your mouth open so the air isn't expanding too much, then you'll feel hot. But if you purse your lips so the air is rapidly expanding when it leaves your lips, then you'll feel cold. So you can do this experiment either here or in the privacy of your own home. The other experiment you can do is you can test the spring or the rubber band idea. Again, your lips are very sensitive temperature measurements. Okay? You don't always carry around, sensitive physics laboratory equipment with you, but your lips are actually much better than most things at detecting temperature. And so if you take a rubber band, you touch it to your lips, and it feels cool, and if you rapidly stretch it and touch it to your lips, then you should be able to notice that it heats up. So again, you're probably not all carrying rubber bands with you, but again, this is something you can do at home to test this out. So springy things effectively have a negative pressure. For those of you who are more physics class oriented, this is just basically second law of thermodynamics, that you have the change in energy is minus the pressure times the change in volume. du is minus pdv. So instead, if you're stretching something and it heats up, then that minus p actually has a plus sign, which means the pressure is effectively negative. So in any case, springy things basically have negative pressure. So the question is, well, on a cosmic scale, what are we talking about as far as springy things go? Well, Einstein taught us that the structure of space-time itself is springy, that you can think of the curvature of space-time as being equivalent to a force of gravity. And so he said, let's picture space-time as a big rubber sheet, and that if we drop a mass on that rubber sheet, it causes the sheet to dimple, to dip down, and then if we roll a little object along, it's going to roll into that dimple. There's no force of gravity. All it's doing is following the geometry of space-time. So Einstein said, forget about what you learned about Newtonian forces at a distance. It's all geometry. It's all curvature of the rubber sheet of space-time, the stretchiness of space-time. But remember, Einstein said E equals mc squared. Every form of energy contributes to the gravitational mass. Suppose you made this bowling ball not out of ordinary atoms, but you made it out of something with a big internal pressure. So for example, radiation, light, has a positive pressure. So if you could somehow make a big ball of light and drop it on the rubber sheet, you would find that it would dimple the rubber sheet more than the mass would, because it has that extra pressure, that extra gravitational attraction. But we want something with negative pressure. So the idea is that we want to make a bowling ball out of something with this negative pressure. We drop it on the rubber sheet, and at that point we don't get a dimple, but we get a hill. Now when we roll a little marble along, it's repelled from that. It looks like anti-gravity. Again, it's all just the curvature of the space-time. And so if something with negative pressure could exist, you would get this apparent repulsion, and that would look like the universe is expanding. It would make the universe expand more quickly. So the question again is there anything in physics which could have that sort of negative pressure? And this is not some extremely rare object. The discovery was not only that there is this acceleration in the universe, but it so dominates the expansion that at least 70% of the entire energy content of the universe has to be in this very strange negative pressure form. So I don't think I'm actually getting into it, but the answer, one of the possible answers is quantum physics tells us that space-time itself, I think I do get to this actually. All right, then I'll save it for that. So as I said, about 70% of the universe. So if you look at the pie chart of the energy types in the universe, the stuff that makes us up, so the ordinary elements in the periodic table, as well as the lightest parts of the periodic table, hydrogen, helium, adds up to less than 5% of the whole energy budget of the universe. Then you have things like neutrinos, you have things that have condensed into stars, and so forth. Dark matter, which I won't have time to talk about today, which I call old news stuff because we've basically known about it since the 1930s. It's really come into focus as being an important problem since the late 1970s. We still don't know exactly what it is, but we have very high hopes that within the next 5 years, we will learn quite a lot about it from both accelerator experiments at the Large Hadron Collider and direct detection experiments in deep mines on the Earth. So you should stay tuned to the science news, and I'm pretty confident within 5 years we'll have actually detected dark matter directly. And then there's this new stuff, this dark energy. Again, that's just the name we give to this negative pressure stuff that is causing the universe to expand. Again, the take-home message is, especially for all the students, there's 95% of the stuff that your professors have no idea what it is. Okay? What you're reading in the textbooks only is 5% of the stuff. You're the ones who are going to make the discoveries of the rest of the 95% of the universe. So all the exciting things are still out there for you to do. So here's sort of the summary of what dark energy is. So it makes up almost 3/4 of the energy density of the universe. You could ask, well, how did we miss it up to now? And it was really a question of the technology just not being good enough. You had to have these automated searches. You had to have the detectors, the CCDs that are now on every digital camera, didn't exist in the early 1980s. To be able to see the very faint light to map out the distant universe. So it was really a matter of technology coming together with the science question. So it accelerates the expansion. We know there was an early epoch where that probably happened, but way back in the very tiniest fraction of the early universe. And because it's causing the expansion, it's going to determine the fate of the universe. If it stays around, the universe will continue to expand forever. If it goes away, then the universe may recollapse at some point. So these are just such important, such central questions that I decided this was just not dramatic enough, saying dark energy is this. That instead, you have to put the exclamation points there. Because this is just so exciting science. Okay? We're talking about 95% of the universe still to be discovered. We're talking about essentially anti-gravity. We're talking about gravity acting in a repulsive fashion. And we're talking about a question of the fate of the universe. This is something that you can really interest people. You sit next to someone on an airplane and you say you're working on this, you're going to have someone to talk with the whole time on the flight. So that's why I call this triple exclamation point science. Okay, it's just so fascinating. So it's the most abundant stuff, but it's also the weirdest stuff, this negative pressure. So Einstein actually had a theory for this way back in 1917. He called it a cosmological constant. He actually introduced it for the wrong reason. He then got rid of it again about a dozen years later. The question is, should we bring it back again? So one of the reasons why we shouldn't bring it back is when you try to calculate how big the effect of Einstein's cosmological constant is, you're off by a certain factor. And I always tell my students that if they hand in a homework where they're off by that factor, they're not going to get full credit. So as physicists, we've got to say, well, we can't give ourselves full credit for solving it just by saying it's Einstein's cosmological constant. We really have to understand why the amount of energy there is so different from what we expect. Or we should say, well, okay, that's just not the answer. We have to come up with a new answer. So physicists admit they're wrong, but they modestly say, well, it's a fine-tuning problem. So it's like, you can't quite get the radio station in, the reception's not quite so good. You have to fine-tune it a bit, but there are a number of zeros there you've got to fine-tune away. So again, Einstein does not approve of this. I'm going to actually skip over this part. I think all those zeros is a good enough reason for saying there's a problem. So if you go beyond Einstein's cosmological constant, you can ask, well, where should I look? What area of physics? So one thing you can ask is, we're talking about basically the structure of space-time itself, what's called the vacuum. Just when you take all the matter, all the energy away, what's left? Just space-time itself. Quantum physics deals with the vacuum, deals with the energy that is there when you've taken away everything that you thought was energy. And so the question can be phrased in this very provocative way. Does nothing weigh something? You've taken out everything from the universe. Are you left with still this energy, this negative pressure? So it could be Einstein's cosmological constant, or it could be these other quantum field theories, string theory, or what's called quintessence. Or instead, maybe we should say, well, we just didn't understand gravity well enough. We don't have to introduce some new particle or new field. We just didn't understand what gravity is actually doing. And one of the explanations for this is trying to unify quantum physics with gravity. Nobody's succeeded in doing that yet, but maybe if someone does succeed, that will carry with it an explanation. Or people also like the idea that there can be more dimensions besides the 3 space and 1 time dimension. And that if you add these extra dimensions, that maybe this can explain it. And so I like to phrase that as this equally provocative question is nowhere somewhere. Okay? Outside the 3 dimensions, what is there? Maybe there are dimensions that can help explain this. And so I'm going to give you a 1-slide summary of all of quantum field theory in 1 slide, and then all of gravitational physics and extra dimensions in another slide. Oh, actually, I guess I'm taking a couple slides to do it. All right, so one of the questions is the nature of space-time. Remember we said that negative pressure can arise from rubber bands or springs. And so the idea is this rubber sheet that Einstein viewed space-time as is basically a whole series of springs. And we can phrase the question then as asking, are those springs static? Are they always the same? And they're always the same height, basically. So that would be Einstein's cosmological constant explanation, where the word constant sort of gives it away. Everything just stays the same in space and in time. Or maybe those springs are different heights and they're all bouncing up and down in some particular way. Is it dynamic? So it varies in time and space. And that's the quintessence explanation of things. So our questions are, how much dark energy is there? We want to measure that. And how springy or stretchy it is. So we take these baby steps. We ask these little questions to learn. We learned in 1998 that there was dark energy. Well, now we want to learn what it is. So here's all of quantum field theory in 1 slide. It's much simpler than you probably thought it was. In quantum field theory, the key word is field. And again, it's what you know about in everyday life. You're very familiar with fields. So you have a field of grass. And you can say, as I walk through the field of grass, if I was extremely bored, I could say, what's the height of that stalk of grass over there? What's the height of that stalk of grass over there? What's the height of that stalk of grass over there? At every point in space, I could define a field. I could say, what is the height of that field of grass? Quantum field theorists give that a fancy name. They call it a scalar field theory. At every point in space, they have one number. What's the height of the stalk of grass? Okay? That's scalar field theory. That's all you need to know about that. Or, maybe as I walk through the field, I stamp out a pattern in the field of grass. I bend the field of grass, so they not only have height, but now they're stamped down in some direction. Maybe I stamp them all in the same direction. Maybe I make a crop circle, some special pattern. Here's a nice crop circle picture. So now there's not only a height of the stalk of grass, but there's a direction that it points. So that's what a vector field is. So that's quantum field theory. Again, everyday life, you know this already. So you can ask, can these fields give rise to the acceleration of the universe? So again, scalar fields are actually very popular as an explanation for doing this. For one thing, mathematically, they're very simple. For another thing, many theories, you sort of automatically get scalar fields. And so the quintessence explanation uses scalar fields. Some people are working on vector field explanations as well. How about extra dimensions? Again, this is something that you know about in your childhood. If you hit a tuning fork, the sound radiates off in all directions. And so it very quickly fades off with distance. But you've all done an experiment in quantum gravity as children, or probably most of you have. The game of telephone, where you connect tin cans together by a string. Now the sound doesn't spread out. When you whisper in one can, it doesn't go off in all directions. But the vibrations get transmitted along the string. They're localized to this one dimension, and so they can carry much further. So that's the whole idea of extra dimensions, that the number of dimensions that you're propagating the signal in affects the strength of that signal. And so the idea is, on large scales, if there are extra dimensions, gravity may be able to leak out into higher than 3 dimensions. So if it only propagates in 3 dimensions, then it has a certain strength. But if it propagates off into a 4th dimension, you lose that, then gravity becomes weaker. If you're weakening gravity, then the universe is not going to collapse, but it will continue to expand, and you can actually arrange things so that it expands faster. And so acceleration of the universe could be related to gravity getting weaker on large scales. And again, that can be related to how many dimensions is the force of gravity actually propagating, is actually moving in. So that was quantum field theory, and now this is extra dimensions in a slide each. So let me get back to supernovae and talk a little bit more about the observations. So a supernova is an exploding star, and as I said, it gets briefly as bright as an entire galaxy, so extremely good lighthouse, basically, that you can see it at great distances away. What a supernova actually is, we think, is that it comes from a binary system, that you have an old evolved star called a white dwarf star, which is in a binary system, and it basically steals some mass from a much larger giant star companion. And as that mass comes in and falls on the white dwarf star, it heats up the core. So you have the mass coming in, increasing the pressure in the core, increasing the heat in the core. And eventually you reach a limit. You approach this limit called the Chandrasekhar limit, which I guess I don't have listed up here. But it's a fundamental limit from nuclear physics, which says you just can't add more mass than this. The star can't support it. It'll just blow up. And so we think that's what a supernova is. And so we think you get a pretty standard explosion because of this nuclear physics. And so here's the supernova going off. Okay? And then you can see it from across the universe. So here are some actual examples. So again, because it's a transient event, you have to look at the sky again several times. So you look at the sky and you say, okay, there's a galaxy there. You go back and you look at it and you say, wait a moment, that galaxy changed. It got an extra little bit of light associated with it. And then you go back later and maybe that bit of light went away. And you say, okay, that might have been a supernova. Ideally, you do better than that. You look at it, you say there's no supernova. You look at it, you say there's a supernova. You call up all your friends. They all put their giant mountaintop telescopes on it. And you actually get a lot of information, such as spectra and so forth, on the supernova. So here's an example of 3 different supernovae. These are so distant that you have to use the Hubble Space Telescope to understand it, to detect them. Okay. So the idea behind supernova, using them to get distances, is again something that you're familiar with from everyday life, or not everyday life, but you've probably seen the luminarias that I know in San Antonio. I don't know if they do that in Houston also near Christmas time, that you put out the candles in the paper bags. And so you can do the same thing with lampposts, that you can figure out if a car is coming toward you, and as it passes each lamppost, you can say, well, if I detected how bright that lamppost was, I can measure its distance. If every lamppost has a 100-watt light bulb in it, the further ones are going to look dimmer. They're going to give off less light that enters your eye, because that light is, again, spreading in all directions. And so you have the inverse square law. The intensity of the light is going down as 1 over the distance squared. And so by measuring the brightness, you can figure out how far away the lamppost is. So same thing with the luminarias, as long as you had a standard candle in each one. Each candle was the same brightness. But the supernova, remember, nuclear physics gives us more or less a standard explosion energy, a standard brightness for them. And so that's why we sometimes call supernova standard candles. We can use them to measure distances out in the redshift. One of the things about supernova, though, is that there's a lot of information in them. There's a rich array of information. So you don't just find out, oh, a supernova went off and it went away. You actually learn a lot of physics from each supernova. So for one thing, all of the heavier elements in the periodic table were created in supernova explosions. From carbon on up, basically everything in this room, except for the hydrogen, helium, and lithium, was once in the heart of a star that went supernova and got spread out through the universe. So we really owe lots of supernovae. We owe our existence to supernovae. And in particular, you produce about 3/5 of a solar mass in nickel. And so that's a lot of nickels. If you actually could gather all the nickel from a supernova explosion, then you would have $10 million. So you'd be pretty rich. So it's not only rich in science information, but it's rich in a practically impractical way. But you also get a lot of science information. So here's an example of 3 main types of information you get from a supernova. So first you get an image of the galaxy that it went off in and the brightness of the supernova. So this is a plot of how bright the supernova is as a function of time. Okay, so a supernova brightens very quickly and then it dims in a pretty predictable law. You also, if you get a good telescope on it in time, you get the energy spectrum of the supernova. And so you can make sure that it's really a 100-watt light bulb in that lamppost, basically. By getting all this information, you can actually make sure that it's a standard candle supernova and use it as a distance indicator. So again, we go back to that picture that I showed, the 1998 discovery, where you had these few dozen supernovae that led to the idea that this curve is not turning down, but it's turning up, that you're getting this acceleration. So we've improved a lot since then. So that was 1998. So the current data, as of about a month ago, we now have several hundred supernovae going much further out in redshift, or back in time, if you like. So the right side here is about 10 billion years back. And you have a lot of teams working on this. It's such an exciting project that a lot of different teams are working on this. And then to help you see this a little bit better, I'm going to average the supernovas. So I'm going to take groups of supernova and average them together in redshift. And so you can reduce the error bars down that way. And you can see that they follow very well this curve of the accelerating universe. And so as we get better and better observations, we're going to be able to actually understand the exact expansion history, and that hopefully will guide us to what the physics explanation. Is it Einstein's cosmological constant? Is it extra dimensions? And so forth. Again, as you look at the really distant supernovae, they're very faint, and also the light is redshifted into the near infrared, which you can't observe through the Earth's atmosphere. You have to get above the Earth's atmosphere. So that's why the Hubble Space Telescope plays such an important role for this. The Hubble Space Telescope can see really deeply, but it can't see very wide. So the Hubble Deep Field, that first movie I showed you, is the equivalent of scanning 1/25 millionth of the sky. So that's a very small fraction of the sky, a very small fraction of the universe. So that's like taking a dozen people from here and saying, okay, that's the same ratio as the entire population of the United States. That if I looked at these 12 people, I could understand everything about the population of the US. Okay, you need a much better sample than that. And so the idea is to have deeper and wider surveys. So let me show you a movie. So this is from a project called Sloan Digital Sky Survey, which maps about a quarter of the sky and maps about 500,000 galaxies. So this is a little old. It's actually almost up to 1 million galaxies now. Can we turn the lights down maybe to get maybe better? This is not on. Let me stop it so you can wait till the lights go down. So this is basically, these are all real pictures of galaxies. They were put together in computer simulation, and so it looks like you're flying through the survey. But each point of light in here is a real galaxy that was observed through the telescope in the right position relative to the other galaxies. So the survey was done in narrow slices, so that's why it looks like there's a concentration here. But you see there's all sorts of different galaxies. There's spiral galaxies, elliptical galaxies. Some are redder, some are bluer. That tends to be the ones with active star formation going on. Now you can start to see the structure where they scanned in several slices of the sky. And then it's going to rotate around so you can see the different slices. So they scanned off in different directions of the sky. Now they're zooming out further, and now they're going to patch in. So these are now the quasars, and then they're patching in the hot and cold spots of the cosmic microwave background, which I haven't had a chance to talk about. But that's the furthest that we can see in ordinary light. You can see the galaxies have only actually sampled a small volume of the full sphere that we can see with light. Okay, so if we want to do better, we need surveys like that to scan vast areas of the sky. And those surveys some are underway, and we're designing for the future. Again, to see the most distant things, we need to go to space. And so there are proposals to basically build a wide field version of the Hubble Space Telescope. So NASA is working together with the US Department of Energy to build this joint dark energy mission to really explore what is the physics behind this accelerating universe. So let me just sum up. There's incredibly interesting questions that are facing us. And again, for the students in the audience, you're the ones who are going to be the research scientists at the time that we start to get the answers to these. So I definitely want to encourage you to pursue these questions. What is this dark energy? Those four forces of nature that I talked about at the very beginning, why are there these steep hills? Are those the only forces there are? Are the three spatial dimensions we know about the only dimensions that there are? How do you reconcile quantum physics and gravity? How do you unify those? And what is the fate of the universe? So these are all fascinating questions, and I hope as you walk around, whether it's up steep hills or not, look at the world around you, that you continue to wonder about these questions and that you realize how you're tied in to cosmology and to the study of the universe. Thank you.
Okay, questions?
One of the magazines that I subscribed to presented an alternative explanation for this accelerating expansion, which didn't require any new physics. What it said was that if the area around us, say within a few hundred million years, has more dense matter than the rest of the universe as a whole, then the local area will have contracted more rapidly as the expansion slowed than the rest of the universe did, and that would cause it to look like the rest of the universe is speeded up.
Mm-hmm. Right, so this is called an inhomogeneous universe explanation. Sometimes called the local void explanation.
Yeah.
So if you want to explain that supernova plot, if you want to explain basically that rise and fall, then that explanation in fact is possible. There are two flaws in it. One is that we have to be situated extremely close to the center of that void. If we're off-center, then we will not see that sort of fall. We'll see different things in different directions. And so that leads to what's called the problem of Copernicus. Why should we be at the center? So that's one possibility. The other flaw is when you take into account all the other science data, for example, the galaxy surveys, the movie that we just showed flying through, when you map out in different directions, we see no evidence of such a large void that you would require to explain the supernova data. So when you take not just the supernova data, but the supernova plus the cosmic microwave background data, plus the galaxy survey data, when you put everything together, that explanation doesn't actually hold up. And that's why we think we actually do need either a new law of physics or a new particle, new field, something like that.
Another thought on that subject. Gravity is pretty weak anyway. So why do we need, once the universe gets big enough, will cease to function with gravity power. It becomes zero virtually. Therefore, the universe will continue to accelerate. We don't need it to get weaker as time goes on, and just remain the same. Is that one way of looking at it?
So the universe is such a big place that two of the fundamental laws, forces of physics, the nuclear forces, the strong and the weak, play no role. They're both very short-scale ones. So the only other long-scale force that we know about is electromagnetism. But we think the universe is, on average, extremely neutral. That for every positive charge, there's a negative charge. And so even though gravity is so much weaker than the other forces, on the cosmic scale, it's still the dominant one because basically electromagnetism cancels itself out. Okay, because you're overall electrically neutral. We know gravity exists. We see galaxies colliding, that they're falling toward each other. We see stars orbiting around galaxies. So we know that gravity hasn't gone away, which that would be a mystery in itself. What would cause gravity to change its behavior? But again, we see these evidences that gravity in galaxies and clusters of galaxies seems to be operating the way we expect. It's only on the largest scales, the truly cosmic scales, that it seems to be getting weaker. And we can actually measure how much it would need to be weaker. We know it can't have completely gone away. It just has to equivalently get weaker enough to cause that acceleration.
I have a question for you about the redshift time, this expansion factor. Okay, my understanding is that one element of Einstein's theory of gravity was that large amounts of mass will redshift light. How do we know that this is not happening?
Right, so there's actually several types of redshift. What you're talking about is a gravitational redshift. So that we can actually measure here in the lab, the mass of the Earth itself will cause a very, very tiny shift in the frequency of photons. So this was the famous tower experiment, Pound-Rebka experiment that we can actually measure. So we think that in certain parts of the universe, such as very close to black hole horizons, that in fact you would get exactly that redshift. On cosmic scales, there aren't dense concentrations of mass, right? The galaxies are pretty spread out. There's a lot of empty space in between. We know that expansion gives rise to a redshift. As a moving object gives rise to a Doppler shift, an expansion, a stretching, will give rise to a cosmological redshift. And in fact, by looking at how the intensity of light changes as a function of distance, you can actually separate out other explanations, such as a Doppler shift explanation or a gravitational redshift explanation, from this cosmological redshift expansion. So there are other elements that go into that to tell us that it is really due to an expansion of the universe.
See, I was wondering if it could be additive as you look out, additive effect of mass as opposed to redshift.
So again, Einstein's effect, you really have to be in pretty extreme gravitational fields. So really only near black holes is it relevant. Neutron stars, you can sort of get a 10% effect, but black holes are what will give you the sort of factor of 2-ish effects. So again, in the universe, it's a pretty empty universe. It's a pretty low-density universe for the most part.
Your slides, it sort of implied the dark energy, dark matter was out there rather than in here. And if they're relatively uniform, why isn't it here? And if it is, how do you detect it?
Right. So basically, the Earth's a very small place in the universe. So yes, there is dark matter. Yes, there is dark energy. But there's such a small amount. So if you ask, what's the effect of the dark energy in the entire solar system, in the entire sphere of the solar system, on the orbits of the planets, it turns out that the force from sunlight is, from just 3 hours of sunlight, is stronger than the force due to all the dark energy in the solar system. Because the solar system is just really small. The dark energy level is very low, but when you add it up over enough space, then it becomes this huge effect that dominates the expansion. For dark matter, we do indeed try to detect it in experiments. I mentioned the experiments in the deep mine. Again, the chance of a dark matter hitting a nucleus in your experimental apparatus and seeing a signal is very, very small. And that's why up until now, there have been no definitive detections. But people are very hopeful. And as I said, I think in the next 5 years, the experiments are getting large enough and sensitive enough that we should be able to detect the dark matter that streams through the solar system in just this way.
Can I follow up on that question in a way? Are you familiar with the Pioneer spacecraft tracking anomalies?
Yes.
Is that possibly a manifestation of some of this physics?
So, I know astrophysicist at Jet Propulsion Laboratory who's actually spent quite a few years unearthing the old tapes, finding someone who could actually read the old tapes of the Pioneer tracking and so forth. They think they've explained about 60% of the anomaly due to the fact that basically the heat flows on the spacecraft are not uniform. Okay, so they had this basically a nuclear generator off on a boom in one direction. That's bouncing off the spacecraft, the radiation from that. So any push like that that's not balanced, that's asymmetric, can contribute. But they didn't explain 100% of it. But you start to wonder, well, if they've gotten rid of 60%, isn't there another effect that they haven't taken into account that could explain the rest? The other thing is not all spacecraft have shown this anomaly. And even the sign of the anomaly, whether it attracts toward the sun or pushes away from the sun, is actually different between different spacecraft. So it doesn't seem to be related in any way. No one's quite sure, is it a real fundamental physics anomaly, or is it just understanding all the physics of the heat flows, of the asymmetries of the spacecraft, and so forth. But as I say, they've actually spent years and years looking into this. It's incredibly complicated. It's amazing.
Getting back to dinosaurs.
Yes.
The School of Thought, Francis Crick, of course, who was in the DNA world, he spent the rest of his life thinking about the origin of life on Earth being from meteorites, asteroids. And the School of Thought that the dinosaurs were not wiped out by the asteroid completely, but by the infection from the asteroids or the meteorites from that onward. It took several million years. It didn't happen suddenly. So evolution could it not, from bacteria, viruses, and so forth.
Right. So it's certainly true that if you have, there are going to be several weakening agents. So again, you're basically stressing the ecosystem you throw up all this dust and so forth. If there are other factors, such as maybe the impact also caused great volcanism, volcanoes exploding, other biological explanations, you could have had several factors. The idea of viruses from outer space, I'm not really sure what the current school of thought. Could they actually survive? Would they interact with Earth life in the appropriate way? That's not my field at all, so I can't say anything about that.
I will offer one comment on the paleontological evidence that we have thus far is that not just the dinosaurs, but 75% of the species wasn't millions of years. It was a blink of an eye. It was basically as fast as the geologic record can be parsed.
Right. I know that, for example, a lot of marine life also went extinct. So you would need to factor that into whatever the explanation was. Yes?
From your perspective, what are the technologies that we need to solve some of these puzzles? You mentioned earlier that we did not have enough technologies to detect some of these in recent history. So from your perspective, what are the technologies that we are lacking now or we need to develop to get to this point?
Right. So for this really distant object sort of astronomy, the sort of things that you need are, again, we're sort of passively accepting the light that comes to us. So you need to collect a lot of that light to see the faintest objects. You need to build bigger and bigger telescopes, which means giant mirrors or segmented mirrors. Many of the next generation of telescopes are going to many different segmented mirrors. We need more sensitive detectors. So I mentioned the CCDs, these charge-coupled devices, which now go into digital cameras. Those get more sensitive, better able to detect the infrared light. Again, because of the redshift, the light is redshifted into the near infrared. So those are very important, and those have actually gotten a big boost from night vision devices. So there's actually a lot of spin-offs between astronomy and military uses as well. Those sort of technologies, computing power is incredibly important. The next generation of experiments will bring in huge quantities of data, terabytes of data each night. You have to actually be able to process those, sometimes in real time, to find things like exploding supernovae. There's a huge variety. There's not only optical telescopes, there's radio telescopes. People are developing gravitational wave observatories, neutrino telescopes. It's incredibly exciting, the fields out there. And as you say, technology really does drive an enormous amount of it. Yes?
On the issue of gravity, there's been, I think, Milgram proposes that perhaps over large scales, the exponent of the gravitational equation.
Right.
Has that been discredited?
So, right, the idea is that the inverse square law of gravity, the gravity dies off with the square of the distance. His suggestion is at very low accelerations, very weak gravitational situations, that could change. The original theory did not work for what's called gravitational lensing. When light goes by a massive object, it gets bent. This was how Einstein's theory was first verified during a solar eclipse, seeing the bending of light by the sun. The same thing happens with light going by galaxies. And Milgram's theory didn't explain that. In the last 5 years or so, there's been a much more complicated theory that incorporates that, but it still doesn't explain all of the observations. When you change that law of gravity, you still need to have you need to have some mass in this place to get a certain deflection. So what the dark matter explanation says, sure, you see some mass in this place, but there's also some dark matter over in this place, and that changes the deflection as well. Changing the law of gravity can't help you if there was no mass there at all. And so there's an example of something called the bullet cluster, where two clusters collided with each other, and then you look at the lensing, you look at where is the mass, so you can, because they collided, you can see them in X-rays. The gas has been shocked and is very hot, gives us X-rays, you can see where that is, and then you map with the gravitational lensing where the mass is, this dark mass, and you find that they don't match up exactly. And so my feeling is that you cannot simply change the law of gravity to get rid of dark matter. You might be able to for dark energy, but the Milgram sort of theories, my bet is they're going to fade away in the next few years.
Okay, any other questions? All right, let's thank our speaker. And I hope to see everyone next week. We're going to have Dr. Talent here, and he's going to be talking about removing orbital debris. And there are a couple sign-in sheets that are running around, so appreciate if you could sign in, and if you'd like to give us your email address for future talks.